referring to itself and saying it's unprovable. So that's why there's a problem. Okay. So, but people didn't really know what to make of this, right? So then comes in 1930. So this is very, very surprising. So I would say surprising here. Shocking. Terrible shock. Now, then comes Turing, and Turing goes, my reaction as a child reading this proof is I follow it step by step, but I don't like it. Doesn't appeal to me. Which is good. If I had said I like it, it's wonderful finish, I go on and become a molecular biologist and start up a biotech company, and now I'd be rich, but I wouldn't have done any work in this area. So then comes Turing. Now, I prefer Turing's approach. Turing goes more deeply into this. Turing is he starts talking about computers. This is the point. Turing, in a way, here's what he do. He has to invent the computer. Because Hilbert is talking about there should be a mechanical procedure to decide if a proof is correct or not. So Turing says, well, what Hilbert's really talking about is a computer program. But first of all, you have to say what a computer is. That's a Turing machine. So all of this is in a paper of Turing's in 1936 when there were no computers. So it's a fantastic piece of work. And I would like to claim that this is the invention of the computer. These were general-purpose computers. Okay, that was the idea on paper. So the idea is, what Turing shows is, in fact, that there is a relatively concrete statement that escapes the power of mathematics. This sounds pretty strange, but what Turing says, well, here are computers. We now think of computers as physical devices, right? So they're almost like something in physics. It's a machine working away. It's somewhat of an idealization, but you have this machine working, and Turing discovers the halting problem. So the halting problem says there's no way to decide if a computer program will eventually halt. Now, obviously, to decide whether a computer program will halt is the easiest thing in the world. You run it, and when you run out of patience, that's it. It doesn't halt as far as you're concerned. Who cares? You can't wait any longer, right? But what Turing showed is if you put no time limit. Now, this is very abstract mathematics. I mean, in the real world, there's always a time limit. You can't run a program 1,000,000 years, 1,000,000,000 years, 10 to the 10 to the 10 years. So if you put a time limit, the halting problem is very easy to decide. In principle, you just run the program that long and you see does it halt by that point or not. But what Turing showed is if you put no time limit, then there is no solution. There's no way to decide in advance whether a computer program will halt or not. If it halts, you can eventually discover that by running it. The problem is to realize you've got to give up. So there's no mechanical procedure that will decide in advance if a computer program will halt or not. And therefore, it turns out that there is no set of mathematical axioms in Hilbert's sense that can enable you to prove whether a program will halt or not. Because it turned out that if you could always prove whether a program will halt or not, you could run through all possible proofs in size order, check whether they're correct, and eventually either find a proof the program's going to halt or find a proof it's not going to halt. And this would give you a way to decide in advance whether a program's going to halt. Now, in practice, running through all possible proofs requires an astronomical amount of time. Imagine how many proofs are there that are 1 page long. You'd never go through them, even 1 line long. But in principle, you can run through all possible proofs in size order, check whether they obey the rules. Hilbert is talking about formal axiomatic systems. So if you had a formal axiomatization of mathematics that enabled you to always prove whether a program halts or not, that would give you a mechanical procedure by running through all possible proofs in size order to decide whether a program will halt or not. And Turing showed that you can't do it. His proof, by the way, is equivalent to Cantor's diagonal argument, which all these ideas are connected, but there's no time to go into that. So I think that this makes the limits of mathematics seem much more natural, because we're talking about a question about a physical device. It's a computer. You fantasize a little bit. You make it a theoretical computer, a computer that can go on forever, that never breaks down, that has as much storage as it wants. So if the numbers get too big, it can keep going anyway. But that's not too much of a fantasy. We have devices like that everywhere, right? So it sounds much more concrete. The limits of mathematics, as shown by Turing, sound more difficult, more serious, more dangerous than the ones that Gödel found. And this is the invention of the computer for this crazy kind of theoretical argument, by the way. So you don't see billions and billions of dollars of technology in this 1936 paper, but it was all there in embryonic in embryonic form. As von Neumann kept emphasizing, by the way, that the universal Turing machine is really the notion of a general-purpose programmable computer, the idea being that you had machines that did calculation before, but they did special-purpose calculations. You know, machines for doing multiplication or adding machines, calculating machines. Friedens they were when I was a kid. But the notion of a computer is Turing's notion of a machine that can do what any calculating machine can do, and that's the idea of software. It's a very general-purpose machine. You know, it's a flexible machine. So it's really there, von Neumann kept saying very clearly in Turing's paper. So you have this whole technology there. And in fact, Gödel's paper, as I said, is Lisp. There's a programming language hidden in it, and here there's a programming language explicitly, Turing machines, which is a machine language. It's actually a very bad machine language. It's a machine that nobody would, no person in their sane mind would want to program. But Turing wanted to keep it as simple as possible, obviously. If his paper had included a manual for the machine language of a real machine, it was hopeless, so he had to make a model. Okay, so now what happens with all of this? What happens with all of this is that Hilbert dies, the Second World War comes, and when I'm a child around in the 1950s, I could still read essays by Hermann Weyl and John von Neumann talking about all of this. But the world was clearly going in a less philosophical direction, right? Going in the direction, you know, things were going downhill rapidly until we're all billionaires with our web startups. So the people were less concerned about philosophy, and computers were becoming a technology, and Turing was very involved in that. And so was von Neumann. But stupidly, I wanted to understand this, and so in a way, I'm stuck in this 1930. I had never got past that stage. So what is it? What happened? What happened is, with me, is that I couldn't accept the fact that everybody said, who cares? Now, it's true that in practice, I mean, there are a lot of things in life besides foundations of mathematics and epistemology. You know, there are things like having a family, earning a living, wars, politics, you know, having a house, lots of stuff out there, obviously. But what I couldn't accept is that even in the world of pure mathematics, mathematicians were saying, so what? In practice, we should do mathematics exactly the same as we've always done it. This does not apply to the problems I care about. That's basically the reaction to all of this. At first, there was terrible shock, and then it went from one extreme to another. There was, who cares? It's, you know, people would say it's obvious, or it's irrelevant. This has no impact in practice in how we should do mathematics. And I was very unhappy with that. I was obsessed by this, and I had an idea. When I was a kid, I really wanted to be a physicist. And a lot of mathematicians say, I never made it into mathematics, really. I never succeeded. I'm still stuck. I wanted to be a physicist, and I got corrupted by a lot of ideas from physics. Now, one idea from physics that was also, you know, while all this crisis was going on in mathematics, there was a parallel crisis going on in physics, which actually started in the 20s. The key date is 1924. And that's quantum mechanics, right? And that's the whole question of uncertainty and randomness in fundamental physics. So when I was a kid, besides reading essays talking about Gödel's incompleteness theorem and saying, oh my God, there were also essays saying, well, what happened to determinism in physics? What happened to predictability? Can there be randomness? Does God play dice? You know, does God play dice? Einstein said no. God doesn't play dice. He hated quantum mechanics.